We're going to find the eigenvalues. We're looking for the determinant of a minus lambda I to be equal to 0. So I'm going to skip straight to writing everything in our matrix. So I'm going to have 1 minus lambda, 5, 6, and 2 minus lambda. And if we set that determinant equal to 0, it means I'm solving 1 minus lambda times 2 minus lambda minus 30 is equal to 0. So if I multiply all of that stuff out, I think I'm going to end up with a positive lambda squared, a negative 2 lambda, and another negative 1. So negative 3 lambda, and then plus 2 minus 30. So lambda squared minus 3 lambda minus 28 is equal to 0. And I think that means I'm going to get a 7 and a 4. And I probably need my 7 to be negative and my 4 to be positive. If you don't love factoring, you can just throw that into quadratic formula. That's okay too. So I'm getting eigenvalues of 7 and negative 4. Is that what you all got? So eigenvectors are never unique. But to find the eigenvectors, we have a couple of options. We can either go back to that fundamental relationship that says that A times my eigenvector would equal lambda times the eigenvector. Or we can skip to the part that says A minus lambda I times that eigenvector is going to have to be our 0 vector. So if I go with this version and I start with a lambda of 7, then in matrix form, plugging in 7 for my eigenvalue, I would have negative 6, 5, 6, negative 5 times my xy vector has to be equal to the 0 vector. And as a reminder, we are not looking for x and y to be 0, 0. We are looking for the interesting solutions to this. And each line should tell us the same piece of information. So in this case, that says negative 6x plus 5y, if I read across the top line, is equal to 0. Or if I read across the bottom line, 6x minus 5y is equal to 0. And they're telling me the same thing because if I multiply the top row by negative 1, I get the same thing as the bottom row. Couple of different options for how to proceed, but given some of the web work homework, I'm going to proceed by saying all of my vectors live on this line. So the equation of that line, if I rearrange that, would say y is equal to 6x divided by 5, or 6/5 x. And that's the actual equation of the eigenline. And we can pick any point on that line to be our representative eigenvector. Anyone want to offer up what they chose? Sure. I don't like fractions. So that's not true. That's not fair. I do like fractions. I feel like I'm more likely to make a mistake further into the problem if I choose fractions. So if I didn't want to choose fractions, I might choose 5, 6. The other reason that I kind of like not choosing fractions is that if I had to sketch that eigenline, now I really just have to think about the vector that moves 5 to the right and up 6. And put that eigenline in there. So that was when lambda was equal to 7. For our other one, if I set lambda equal to, what was our other eigenvalue, negative 4. So if I do the same thing, but with lambda equal to negative 4, 1 minus -4 sounds like 5, so I've got 5, 5, and 6, 6 times xy is equal to 0, 0. Doesn't really matter which line I write out, so if I take the top one, 5x plus 5y is equal to 0, then y needs to be equal to -x. And we can choose any eigenvector we want. No fractions this time. If I just choose 1, -1. And again, if I were graphing the associated eigenline, it would look like this. So my matrix, once I've got my lambda i's in there, I've got -1 minus lambda, -1, 1, -1, minus lambda. So if I set that determinant equal to 0, I've got -1 minus lambda squared plus 1, because I've got minus a minus 1. So that's going to look like lambda squared plus 2 lambda plus 1 plus 1. Does that look like what you all have? So lambda squared plus 2 lambda plus 2 is equal to 0. It doesn't factor, so I'm looking to use quadratic equation. So my lambda is going to be equal to -b plus or minus the square root of b squared. So 2 squared is going to give me 4 minus 4 times a times c. And that whole thing will be over 2a. So if I clean that up a little bit, inside those parentheses, I think I get -4. So I've got the square root of -4 and then all over 2. So I'm going to rewrite that. I'm going to break this up. So I've got -2 over 2 plus or minus. Since the square root of 4 is 2, that's going to be 2i over 2. Or I get -1 plus or minus I. So those are my eigenvalues. Did you get the same thing? Cool. Okay, so let's go ahead and find the eigenvectors. And usually I find that this is the messy part that can throw people off. I don't think, honestly, we're going to have to do a ton with the complex eigenvectors, but we definitely do have to know them because we will be solving systems of linear differential equations, and we are going to get some with complex eigenvalues. Okay. So if I choose the eigenvalue of -1 plus I, and I go to find the eigenvector associated with it, I'm plugging it into my matrix. So I've got -1 minus -1 plus I. I'm going to take it slow. -1, 1, and -1 minus -1 plus I. So that's all inside of my matrix times my generic vector is going to equal 0, 0. So if I go across the top row, I've got -1 and minus -1. So those are going to go away. My minus sign is going to distribute in. So I've got -I times x minus 1 times y has to be equal to 0. And if I look at the bottom row, that would say x, and then I've got a -1 minus a -1, that goes to 0 again, and then a minus I, so minus I times y is equal to 0. They should tell me the same piece of information. I'm going to take that top one and rearrange that to say y is equal to -I times x. So one possible eigenvector here would be to let x be equal to 1, and that would make y -I.
But how did the two lines stay the same?
So let's look at the second row. And if I look at the second row, well, first of all, are you okay with my one negative I? Okay, so I'm just gonna check, is that also a solution to the second row? So let's check. So if it's also a solution to the second row, then when I plug in 1 for x, I would get 1. So I'm going to have 1 minus I times negative I. We good so far? And I want to know, is that equal to 0? Because I'm checking, is it really a solution? So this is the same as 1 plus I squared. But if I is defined to be the square root of negative 1, then I squared is negative 1. So this is 1 minus 1, which is equal to 0. So it is a solution to both.
What, I was getting confused that saw that for y equals.
So if I solve this to say y equals, I would have like x is equal to I times y. So I would have y is equal to x divided by I. So fun fact of complexness. These are the same because if I wanted to get rid of this fraction, I could multiply this. I can multiply the top and the bottom by I. So now on the top, I would have ix, and I squared is negative 1, so that would become negative. So it's harder to see, but they are the same. Yes, I'm going to tie the eigenvalues, eigenvector stuff together with the differential equations stuff. So we're kind of throwing it all together so that we can solve systems of linear differential equations. Okay, here's my like fast forward version of some of the vocabulary. So a system of differential equations just means I have more than one. That's what makes it a system. Differential means they have to have derivatives. Equations mean they have to have equal signs. That's it. That's your quick version of the vocabulary there. So let me tie this back to what was the equation I gave us before? Okay. Suppose that I had a differential equation that looked like x plus 5y, 6x plus 2y. So this is a linear system of differential equations because each of these are linear, meaning my powers of x and y are 1. We just have constants times the x's and y's. Just like when we started to talk about functions in 3 dimensions, we defined a linear function as one that no matter how many variables I have, the variables are always raised to an exponent of 1 and possibly multiplied by constants. We're going to now blend that with our tools for rewriting linear equations. So I'm going to blend this to take this part on the right-hand side and say, oh, well, I can write that as a matrix of coefficients times a vector x, y. And if I can do that, I can also write the left-hand side as a derivative with respect to time of my vector x, y. So far, so good? Okay. Now, we were just talking about phase lines and autonomous differential equations. And if I want to find the equilibria of an autonomous differential equation, what do I need to set the derivative to? Sweet. So I'm going to set that. Oh, question first. Yes.
Can you explain how you get it set up like that? Just conceptually.
The left-hand side or the right-hand side?
Both.
Cool. So on the right-hand side, if I were to do this matrix multiplication out, I would get back to where we started. On the left-hand side, this is just telling me to apply the operator to both the X and the Y. We could also write the left-hand side and just keep the operator in there and have that inside. That'd be fine too. Yeah, I was maybe being a little bit lazy, trying to skip a little bit of writing, but yeah, that would also work. Okay, so equilibria happen. Before, when we had y prime equal to 0, right? So our differential equation-y version of that, if I have a system of differential equations, means I need this part to be equal to 0 for equilibria to happen. I'm giving you the fast forward version of yesterday. What's the determinant of my matrix? Is it 0? Which means this is invertible. And if it's invertible, then my only solution is that X and Y are 0.
But why? Why is it?
Okay.
Because we want that to be 0. Okay.
Because essentially I've got something that looks like 0 time is equal to a matrix times a vector. And if A is invertible, then I only get the boring solution that X is 0. So for a linear system of differential equations, we only ever have the boring equilibria.
And you can't like set terms.
Well, I can't set the determinant to 0 if I like already have values in there. Yeah. So for equilibria to happen, X has to be 0 and Y has to be 0. Now, we're going to do some nonlinear differential equations next week. And when we get to those, we're going to have more interesting equilibria. But for right now, if it's linear, if I can write it as a constant times X plus a constant times Y for both of the equations, my only equilibrium is going to be 0, 0.
Unless.
Oh, true. Unless the determinant is 0 here. Yeah. Okay. Now that we got that framed up, next question we should ask ourselves, okay, so when we were talking about autonomous differential equations, after we found equilibria, we had to determine the stability. So now we have to be able to determine the stability for a system of differential equations. And this is how we're going to tie this in. So I promise we're going to loop back around and I'm going to pull it all back together. But we're going to go on a little ride first. And part of my little ride is going back in time to chapter 14. If I told you that dy dt was equal to 3y, could you solve this? Yeah, I'm like, you can probably solve this thing in your head at this point, right? So 1 over y dy equals 3t, 3 dt, integrate both sides, ln y. I'm doing this super fast because I know we got this part. 3t plus a constant, so y is equal to ce to the 3t. Yeah, so far so good? Okay. This is the big leap part. I've written this system of differential equations in a matrix form so that it looks like the derivative of my vector x is equal to a times my vector x. And this part is equivalent to lambda times a vector x. As long as lambda is the eigenvalue, and as long as x is an eigenvector. Which means that if x is an eigenvector, I have a differential equation that looks like this, where that's a constant, and we already know what those solutions look like. Those solutions look like my vector is equal to some sort of constant times e to the lambda t. I will pause just for a second in case there are questions.
Oh, yeah, okay.
So if I know the eigenvalue and if x is an eigenvector, then it's gonna pop out solutions that look just like our solutions did to a single differential equation.
So basically, the left hand side is just like the dx factor over dt, right?
Yep. So that's kind of the big picture of what we're doing. And the thing is, we know that when we do this, we get two eigenvalues and we get two eigenvectors if it's a 2x2 system. So generalizing this, and I'm sure that Dr. Thomas will spend more time like probably actually proving this out. But I'm going to skip to sort of the thrilling conclusion here, is that if we generalize this, we're going to have one constant that's associated with our first eigenvalue and eigenvector. So I'm going to call that x1, y1. And we're going to have a second part that's associated with our second eigenvector.
How is a matrix? But then you multiply C is one T times that matrix plus that, we get have those two matrices together.
Yep.
Isn't that still y2?
Oh, yes, thank you. Thank you. Okay, so I'm gonna just jump to writing the solution for the one we already solved. Okay, so you'll have to tell me what was the
1, 5, 6, 2.
okay, and we got lambdas of 7 and -4. Is that right? Okay, and you can give me the one with fractions if you want, but what are our two eigenvectors going to be? 5, 6, and 1, -1? Okay, cool. So that means that if I started off with the system of differential equations that looked like x plus 5y, 6x plus 2y, then the solutions to this look like C1 e to the 7t times 5, 6 plus C2 e to the -4t times 1, -1.
And so the point of eigen
Equals 0. What do you want x to be? And what do you want y to be? Cool. So this would be enough information for me to solve for C1 and C2. So if I went through that, I would have 1, 2 is equal to C1. And because I'm doing it at t equals 0, and I am telling you, you're only going to do this at t equals 0, right? Now, in your lab, you might do this for other values of t, but if you have to do it by hand, you're only going to have t equals 0. Because e to the 0 is 1, that makes this convenient. And now I'm just solving a system of linear equations. So 1 is equal to 5c1 plus c2, and 2 is equal to 6c1 minus c2. So if I had to solve those, I'm just going to add, so my c2s go away, and I get 3 is equal to 11c1. So c1 is equal to 3 over 11. A little bit gross, but that's okay. And then I can plug that back into either of the other two equations. I'm going to take the bottom one. 2 is equal to 6 times 3 over 11 minus c2. So c2 would be sure. So this part would be considered my general solution, because it still has the C1 and C2 in it. And then I could write a particular solution. By plugging in the C1 and C2. I'm not going to rewrite that. Okay.
So the volume, since it involves X and Y, that's not autonomous, right?
Oh, yeah, so fun fact, it's still autonomous. So, here's the reason that it's still autonomous. My independent variable was time. So because there's no time in there, it's still considered autonomous. Yeah.
X and Y.
So this is telling me that the only variables that can be involved in my system are X and Y. I just can't have a T. I can have constants, I can have X's and Y's, I can't have a T in terms of it being autonomous. Okay. So we can go in two directions. We could like practice this, or I can jump to the part where we're figuring out stability. Jump to the stability part. Okay. This part you probably actually want to write. If you want to take notes, it's totally up to you. I'm going to keep using the same example since we already found the eigenvalues and eigenvectors and we already have the general solution. I just need more space. Okay. So we started off with dx dt, dy dt. I'm just going to keep writing this dang thing over and over again. And somewhere on here, x plus 5y, 6x plus 2y. We found lambda 7, lambda negative 4. This had an eigenvector of, it was 5, 6. Yeah? Okay. Great. Which means that our general solution looks like C1e to the 7t times the vector 5, 6, and C2e to the negative 4t times the vector 1, negative 1. By the way, the reason that the eigenvector that you choose doesn't matter is because in terms of finding the solution, it's just going to change what your C1 and C2 are. Like if you choose different eigenvectors, you'll have a different C1 and C2, but when you like multiply them all together, you'll have the same answer. Okay, so I want to explore some really particular initial conditions. So I want to find the particular solution. If x of 0 is equal to 1 and y of 0 is equal to Actually, let me make x of 0 equal to 2 and y of 0 equal to -2. So if I go to find this particular solution, then again, that 0 in there is telling me that t is equal to 0. So my e to the t parts are going to simplify for us. So I'm going to have 2 -2 is equal to C1 times 5, 6 plus C2 times the vector 1, -1. And if I write that all out, I'll have 2 is equal to 5C1 plus C2, and -2 is equal to 6C1 minus C2. Well, when I add those two together, I get that C1 is actually equal to 0. If C1 is equal to 0, what's C2? If C1 is equal to 0, what would C2 have to be?
Why is it two?
It doesn't matter which one you plug it into. I plugged it into the top one, but if I replace C1 with 0, yeah. Which means that when I go to write my particular solution, because C1 is equal to 0, my particular solution looks like xy is equal to, I get to skip the whole first piece, and then I would have 2e to the -4t times 1, -1. If I wrote that in like not a vectory form, I could also write that to say x is equal to 2e to the -4t and y is equal to -2e to the -4t. As t approaches infinity, where is x going? As t approaches infinity, where is y going? So if I go back to my sketch of the eigenlines, that just told me that along the eigenline associated with this vector, why do I know I'm on the eigenline associated with the vector? Because my initial condition was that x was 2 and y was -2. That's my starting point. And along that eigenline, as t approaches infinity, x and y both go to 0. So I'm traveling along the eigenline and I'm heading into 0. If I had chosen a point over here along my eigenline as my initial condition, which just for fun, I'm going to do, but I'm going to like super hit the fast forward button. So if I pick the point over here, what's that? -2, 2. So if I chose my initial condition to be -2, 2, then when I plug that into solve for C1 and C2, now I have -2, 2 is equal to C1 times 5, 6 plus C2 times 1, -1. Add those together again. And I still get that C1 has to be 0. So I get that C1 is equal to 0 and C2 is equal to -2. And if I think about what's going to happen here, that's going to change the constants, but it doesn't change where my limits are going. because as t approaches infinity, that e to the negative infinity is still gonna take me to 0. So if I start over here, I am also headed into 0, 0. So what do you think? Is that stable or unstable?
It's that's because the next, or 2 zeros is the complete.
Yeah, so like I started on,
So if y was approaching infinity, then it would go towards 0 too. I mean, if y was going to 2, it would be like approaching 0 2.
so this is only if I'm sitting directly on this line, right? Like if I pick another point, life's more complicated. Let's pick another point to show that life is more complicated.
Can we use the graph like that, or can we just use like the face?
So I can't use a phase line anymore because now I have X's and Y's both in the mix. So we're going to shift from a phase line to a phase plane. And we'll play around more with this, but the kind of the moral of the story for the moment is that what determines that stability is actually what's happening in my exponents. And what's happening in my exponents comes from the eigenvalues.
So we're checking the stability of the line or
I'm checking the stability along that eigenline.
stability at any point.
Well, at any point on the line, I'm getting pushed towards 0, 0. So the equilibrium of 0, 0 along that line is stable. Yeah. So overall, the equilibrium, as it turns out, is not stable. Let me keep going for a second. So that's what happened when I chose initial conditions that were directly on this eigenline. And that was the eigenline that was associated with a lambda of -4. And that was the line y equals -x. But we had another eigenline to this problem. And that other eigenline was the one that looked like that had a lambda of 7 and where y was equal to, why am I having trouble? 5, 6, 6/5? 5, 5 6. 5 6 of x.
Or not use.
That'd be great.
It was 6/5.
Okay, that's what I thought. Cool. 6/5 of x. Y was equal to 6/5 of x. So let's pick a point on that other eigenline and see what happens. So if I pick a point on that other line, I'm going to pick the point 5, 6, and I want to see what the long-term behavior is.
But so the equilibrium is 0, right?
Equilibrium is 0.
We know.
We have not determined the stability yet. We have determined that along this eigenline, solutions go to 0. And now I'm going to check along the other eigenline.
We know it's close to 0 because we have t to infinity.
Correct.
Okay.
So now I'm going to check along the other eigenline what happens. Too much paper. Okay. So along our other eigenline, I've got x of 0 is equal to 5, y of 0 is equal to 6. And I'm just going to keep writing that same differential equation over and over again. So our solution, I'm going to have 5 6 is equal to C1 times 5 6, I was lazy, and C2 times 1 -1. I think hopefully we can already see that if C2 is 0 and C1 is 1, we're good to go. But I can write that out if you want. Okay. So this is going to be that C1 is 0 and, sorry, C1 is 1 and C2 is 0. Which means my full solutions then look like e to the 7t times the vector 5 6, or x equals 5 e to the 7t and y equals 6 e to the 7t. So now if I look at what happens as t approaches infinity, where does x go?
0.
Infinity.
Wait, this is, okay. Wait, what? No. Wait, oh, yeah, positive.
Yeah, and so as t approaches infinity, y also approaches infinity. So when I go back and I look at my plane over here, if I start at this point on this eigenline, I get pushed, sorry, gotta find a pen that will actually work. I get pushed out towards x is infinity, y is infinity. And if you're willing to believe me for a second, if I pick a point down here, I'm gonna get pushed towards negative infinity, negative infinity. So this actually, we say that the equilibrium of 0, 0 is a saddle point. By the way, linking things back to fun in chapter 15, how do I know that something's a saddle point?
Because for the same one, it goes up and it goes down.
Sure. And if I had my differential equation,
Wait,
oh,
what?
sorry. If I had my function of x and y, and I was checking to see if my critical point was a saddle point.
Determinant minus.
So let's go back
Wait,
to
0.
negative. So let's go back to my determinant here. If I think about this matrix, 1, 5, 6, 2, the determinant is equal to 2 minus 30, which is less than 0, which tells me that I have a saddle point at that equilibrium. It's all related. Recap, if my eigenvalues are all negative, then everything's going to 0, 0. My eigenvalues are all positive, then everything's going away from 0, 0, or my equilibrium. And if I have one of each, then it's going to be a saddle point. This is my general solution. Looks like xy equals some constant, e to the lambda 1t times my first eigenvector plus c2 e to the lambda 2t times that second eigenvector.
And so lambda is the exponent, so if lambda is negative.
Right. Yeah. So if both of these are negative, then my limit as t approaches infinity for xy is always going to go to 0. And if they're both positive, then they're both going to go to infinity. They could be plus or minus infinity, right? Because my constants could be negative. So this one we would say 0, 0 is stable. This one we would say 0, 0 is unstable. There are other words we can attach to that. So we call it a stable node. We can also call it a sink. We can call this an unstable node, and we can call that a source. Our textbook uses the word sink and source. I don't like those. I like stable node, unstable node. And if I have one positive, one negative, so if they have opposite signs, then the limit as t approaches infinity is complicated. And we have a saddle. Now, other things we haven't talked about. What if our eigenvalues are complex? Right? So it's going to take us some time to kind of work through all of these scenarios.